Alright, welcome to another AQA A-level chemistry video. Today I'm going to be doing a video on condensation polymers. This is going to be a quick video. It's very basic, just me going through the different types of condensation polymers that you're most likely to see, just so that when I go through them in other videos, you don't get confused about the mechanism, what they look like, how you know it, how to actually form these condensation polymers, basic things like that. So this will be a quick video. I'll be talking about very basic mechanisms that you should know for at least for year 2 organic chemistry, and what you should realize about all of these types of condensation polymers. So I'll get straight into it. So condensation reactions can produce polymers if the reagent has two functional groups on either side of the molecule. It can form polyester and polyamides. So that is one thing there. So these two functional group in order to form some of these condensation polymers, you have to have two functional groups, as I said there. So what you notice that with some of these compounds, so they have, some of them will have the same function group. It doesn't have to be different function groups, but they could be the same function group on the same molecule, or could be two different function groups on the same molecule. And we usually call this type of compounds bifunctional groups, or bifunctional groups is the word that usually is given to these compounds. For example, you might get a compound with a carboxyl group on one side, but then an alcohol group on the other side. And because of that, you're able to get, so a single, you can remember this is polymers, right? So just for the monomer, a single monomer unit for some of these molecules, so for example, polyester, on one unit, or monomer as you'd call it, it would have a carboxyl group on one end. So let's say if on the same molecule, we have a carboxyl group on one end, right? And then we have an alcohol group from another group, and then the hydroxyl group from another group, right? And then that would form polyester group. Now on the other side of that molecule, you'll have an alcohol group on that same molecule, right? And then from another molecule, there'll be a carboxyl group to form that polyester. You see in here, because there's two functional groups on the same molecule, that allows two different molecules to bond with that same molecule. So it's not two different molecules. So two of the same type, obviously. I mean, two of the same type of molecule, but they're now bonded to that one molecule on either end to form a polymer. Or in that case, you're forming a what do you call it now? A trimonomer? I'm not gonna try to go for the name for that, but you're starting to form a polymer here. You see, I should have had like a better example, right? But I wish I had a better example to show you what I mean, but actually I could probably just do this here, right? So you have this here, this has this and this, right? And then say we'll have the same, I'm calling this a shape, right? Let's say this is how it is for, this is one unit, right? The next unit will be that, and then you'll have this on this side as well. See, for this one molecule here, two different functional groups here. This is just me trying to make an example of two functional groups, right? But let's say if this bonds to this, so if they have two functional groups on the same molecule, that bonds to that, that bonds to that, and because there's two functional groups on the same molecule, you've now joined all three of these units together to start the polymer chain. And that's what you need to understand about all of these polymers, that they have two functional groups on the same molecule, and because of that, you allow two of the same type of molecule, or two different, or it could be two different. It could be two different monomers to now bind to that one molecule in the middle from either side to form that polymer. Does that make sense? Hopefully it made sense. I'll go through actual examples that you need to know, but that was just kind of like a diagram to kind of give you an idea of what I was trying to talk about, because that principle applies to all of them. Right, so I'll stop waffling now and get straight into synthesis of polyester. So condensation reactions between diols and dicarboxylic acid monomers. Diol is just a molecule with two alcohol groups in there, if that confuses anyone. Hence di, two, and then ol, which means alcohol. So diol, a molecule with two hydroxyl groups bonded to it. It's an alcohol really with two hydroxyl groups to it, and the dicarboxylic acids, you get that right now, just two carboxyl groups on it. A dicarboxylic acid derivative can also be used. So it doesn't have to just be a dicarboxylic acid. It could be a dicarboxylic acid derivative, such as an acid anhydride, and an acyl chloride. The mechanism is nucleophilic addition and elimination, which you should know by now, and I'm going to show you an example of it below. Now, the condensation reaction produces small molecules alongside the polymer, such as water and HCl. So pterylene is polyester synthesized from ethane 1,2-diol and benzene 1,4-dicarboxylic acid. Now, the example I've got below is not pterylene or forming pterylene, but I'm just going to go through an example of a nucleophilic addition elimination reaction and so you have, for example, right? So here's this. I'm going to show you how I would bond two of this molecule together. So if I had this compound, I was trying to bond it to another of this exact molecule, right? So this would be 1, 2, 3. So 1, 2, 3. I call this 3-hydroxyl propanoic acid. 3-hydroxyl propanoic acid is what I'd call this, right? If I wanted to bind it, bond this with another of 3-hydroxypropanoic acid, right? It would be a nucleophilic addition elimination reaction to form a polyester bond. I'm forming an ester bond between a carboxylic acid group and an alcohol group. It would just be the alcohol from the other side. And I could do the exact same thing with this side, just on the other side. It applies to either side that I'm going through. But I'm just going to go through this, which example? Yeah, I'm going through this side first. So, first thing foremost, the hydroxyl group from the alcohol. Don't get confused from the hydroxyl, sorry, the carboxyl or the acid hydroxyl group. That's not the one that actually does the nucleophilic addition elimination. It's not the one that acts as a nucleophile first. It's it's the alcohol's hydroxyl group, which is the one that will act as a nucleophile. It will bind its lone pairs, because remember, technically oxygen could form 3 bonds. It can form 3 bonds if it really wanted to, but generally we just see it as 2. But so the lone pair pairs 3, and it goes to the carbon here, this partially positive carbon atom. I should probably put one of these there. That causes, and then that breaks this double bond partially, forms an intermediate where this partial bond is broken partially. So you then form this intermediate here. But then this isn't really stable. It doesn't like to just have its lone pairs out like this. So you from the lone pair, this double bond reforms. This carbon bond reforms, and the best leaving group would be this hydroxyl group here. This hydroxyl group here will be the best leaving group. So it goes from the bond to the oxygen, and obviously here technically you still have the hydrogen here, so it's got 3 bonds here. Prefers to have 2. Obviously it's not going to go to the hydrogen, so and it's here, it's more positive, so the bonds are going to go towards oxygen, and now you have your ester bond, and you have here an OH minus and H plus as side products. Now we're actually going to form water, but here you now have an ester. Now the same thing could be applied if I just switched it round, right? Think about it, just switch this round, and now I've just gone through, or I've just gone through the other side really. If I did it on this side, same thing. But this idea is just understand the basic mechanism of this and what these polyesters would look like and the kind of themes around these polyesters. So, and I'm gonna keep going now. I'm just gonna. So let's say, okay, so if I wanted to go through what pterylene is, right? So pterylene is what? Ethane 1,2-diol, right? So ethane 1,2-diol. It is this compound here. So and what's the other one? It's some benzene and things like that. Benzene 1,4-dicarboxylic acid. So you have this compound here. So it's a now, I think you guys could actually do this. Now, seeing this, right? Think about it. This whole thing, all of like this here, right? And this here, really it's irrelevant. You could just call that R if you, yeah, you could just call that R. Is that actually going to be needed? The hydroxyl group here. no, actually, I could just even say, I can go as far as saying that is all R. R and R. That's not really going to be relevant to your reaction. If you're doing it from that side, of course, that'll be relevant. But obviously, if you're going from that end, that'll be relevant. But if we're just talking about these two here, right? We're just talking about bonding these two here. Of course, it's a repeating unit where we're going this one, this one, this one, this one, this one, this one. If you're going in a repeating unit. But if we're just talking about these two here, right? I want to pause the video now and try and actually answer this question here. And I'll go through what the actual answer is. But I think a lot of people can do this one fairly comfortably. It's one that comes up in the exam, I think, once or twice, Terraline. So I want people to try and do that. So if I assume you've now paused the video and you've tried to answer that question. Why is it bugged out? Why is it not? What's going on with my screen? Yeah, there we go. So that was just kind of weird. Sorry. Anyway, yeah, that was kind of weird. But I'll go through here. So first of all, the first thing that we're talking about here, right? We have our really, if I wanted to, if I was just, it's only because in the exam you have to represent it in the way that you're meant to, but they might even, in the exam, they might just allow you just to call this R. No, I'll do in the way that, I'm going to assume that they don't allow you to call it R, but if they allow you to just call this rest part here R, you can just literally write this as this here. Because it's not really relevant for what's going on here, but for the sake of the fact that it's important, or they might not allow you to do that, I will do it. But you should know how to do a nucleophilic addition elimination reaction by now. But it's just to show you the point that they may give you an example. They may ask you to do this, and people might look at it first time and say, "Oh, that looks really complicated. That looks really weird. I don't know where to start." I know benzene has some weird things. Benzene, I know I've done a video on benzene, the properties of benzene, but the properties of benzene are not relevant in this question here. All you need to know is just going from here to there. That's gonna go. That's steps. This is all that's happening in your reaction. That's relevant, right? Now we now have this little intermediate here, where you have this is a positive charge now because the oxygen has 3 bonds. The oxygen is now bonded to the carbonyl group. Now this carbonyl bond, so the oxygen is bonded to the carboxyl group, or the carbon is on the carboxyl group. The carbonyl bond has broken, right? Hydroxyl is here, and then we have the rest of our compound here. Right, so first thing in business, so we need to reform this carbonyl bond because that's not stable. How we're going to do that, we're going to have to release, that's the way to, oh, that's not going to happen. You're not going to break this bond, that's just not happening. We can break that. And this this is the easiest part of all of them here. I shall probably put my plus here a bit more, make it a bit more obvious, right? Yes, so that already. Now and that's it, and that's all you've done. That's it. Look at the steps here. Oxygen to, and then obviously I have to do my final the final form, right? But really, you've shown the examiner that you know what you're doing, and that's all the marks. The idea is that I don't want people to get scared at this compound and look at, even if they made this like 100, molecule long compound, whatever, don't get scared by it and say, oh, I have no idea what I want to do. It's you have to just look at what the examiner's asking you, right? All they're asking you is to do the nucleophilic addition elimination reaction. They might not say it. They'll probably even ask you to go as far as just saying name and outline the mechanism. If you know there's a carbonyl group here, forget about all of this. You know, there's a carboxyl group here and a hydroxyl group here, and you're forming a polyester. You know, it's nucleophilic addition elimination. It doesn't matter what the R group is. It could be some, you know, it could be as short as just a methyl group, or it could be as long as some 100 carbon long compound. But at the end of the day, it's the functional groups are the only things that really matter. And those are the things that's actually part of the mechanism that's actually going to react. And that's it. I mean, how would they mark this? 1, 2, 3, and then with the charges that's 4, and the mechanism and overall intermediate that's 5. So probably 5 marks there. But yeah, and then if I actually look at the actual compound, right? This is swapped around, but this is same thing. You see, same thing. Of course, if they ask you to do it as a, they want you to represent it as a if they just wanted this, that's fine. If they wanted to represent it as a repeating unit, of course you have to show your extended lines, and of course that bond would be broken here. So you'd have it will be like this. If they ask you to draw it as a repeating unit. For some reason they don't require you to do the brackets. From GCSE they ask you to do brackets, but in A level they never really ask you for it. But here, look, same thing, right? So CH2 here. That's right. The O extended bond here, again, if they wanted a repeating unit. If they don't really care about a repeating unit, then you're still fine. And that is terylene, by the way. And obviously your benzene group here, the carboxyl groups on either side. Yeah, sorted. So that's polyesters now. Now that I've gone that basic I've shown you the nucleophilic addition elimination reaction. I'm just gonna quickly go through everything else now. Because the same concept applies for. So now, synthesis of polyamides, right? So they're formed by the condensation reaction between a diamine and a dicarboxylic acid. Monomers, again, dicarboxylic acid, the dicarboxylic derivatives can be used instead, such as acid anhydrides or acyl chlorides. And again, the mechanism for the same, I can't speak today. Again, the mechanism is the same as for polyesters, and a small molecule is also produced. Both fibers of Kevlar and nylon 66 are polyamides. You need to know, the one thing you need to know, for example, you need to know the structure of these compounds here. I've given them below, but you need to know these compounds. They're not too difficult to remember. I've forgotten them because I haven't done my A-levels in a long time, but I remember in the exam I made sure to memorize this, and I do believe it was nylon 66 that came up in the exam. But yeah, they're very easy compounds to remember. Anyway, going through this again, polyamides between a diamine and a dicarboxylic acid. So if the amine that they've used here is I'll just go to the same molecule here. I forgot, this is an example where you have 2 different functional groups on the same molecule, and an amine and a hydroxyl group here. So it would be actually, I won't be able to pause video now and try and answer the question for themselves. I forgot to say that. Yeah, pause video now and try and answer the question for yourselves. But I think it's pretty straightforward, isn't it? I was gonna explain this, but like it's pretty self-explanatory now that I've gone through a couple of examples. Again, if you really need help with that video, I'm not going to leave the link in my description because I can't find the initial video where it talks about nucleophilic addition elimination, but I've just gone through already, and you could probably type up on my channel or search somewhere in my channel where it's there. Why have I done that? Why have I done that? Talking too much, that's probably why. There you go. So yeah, so I was just talking way too much there. It wasn't even concentrating. You should be able to do this question fairly quickly. H H, positive charge here. That that would have to go. Make sure the bond's going to oxygen because that's the actual part that's relevant here. Show this compound underneath here. I know you don't have to represent the hydrogens when it comes to... Actually, you know what? It's a skeletal formula. I'm not going to represent the hydrogen. It should be very obvious now that it's not there. For the sake of people realizing what I'm trying to do here, so they can see clearly what I'm doing, that is there. But yeah, nitrogen ionics have formed 3 bonds. And if it needs to be a repeating unit, of course, as I said before, you can just take out the hydroxyl group here, take away a hydrogen here, and then form your extended lines to show that it's a repeating unit if you're talking about a polymer, which is polyamide. So Kevlar, these are the 2 repeating. These are the 2 units I use. So it will be 1,4 dicarboxyl benzene, or what's the name of these? I haven't said it there, but it's a 1,4-diamine benzene, and 1,2-diamine, 1,2-dicarboxyl benzene, 1,2-diamine benzene, and then that's how they form here. I mean, again, it's very easy to see what's going on here. These are just R groups. That's the only thing. That's the only thing you need to think about. That there. Everything else is pretty irrelevant. Unless it's a repeating unit, of course, show your extended lines. And the reason I'm going to put this here is that when I get into to next videos, which will be about biodegradability, check out for that video when it comes out, and subscribe to the channel, obviously, because it helps me out. But the reason why I put this up here, because it's quite important, is because they will ask you questions about why is this polymer, and why are polyamides, why are... The examples I'm going through here mostly are condensation. I mean, it's the video, it's condensation polymers. But why are condensation polymers usually stronger, or why are they more biodegradable? And that's because of the type of intermolecular forces, and these are hydrogen bonds here. Hydrogen bonding here. I thought it's quite useful to have there. Whereas addition polymers are van der Waals intermolecular forces. And that is quite important when you're answering some of these questions about why. If they might ask you to compare, they might ask to give you a 2 or 3 mark question where they'll ask you to compare not 2 or 3 mark, maybe slightly more than that. But the idea is to compare addition polymers, compare the strength of addition polymers, or the melting point or biodegradability of addition polymers and condensation polymers, and it's all to do with this. It's nothing to do with the intramolecular forces or anything like that. It's all to do with the intermolecular forces here, and it's because they have condensation polymers have hydrogen bonding, addition polymers have weaker. I'll go through it in detail when I actually make the video, but ideally, you know that hydrogen bonding is much stronger. Strong bonding between a very electronegative oxygen atom and partially positive hydrogen atom. Very strong hydrogen bonding there, whereas addition polymers have... Have I said that wrong? Have I said that wrong? I think I may have said that wrong. I recorrect my statement now. So these are stronger. The type of bonding is stronger in terms of the fact that hydrogen bonding is a much stronger bonding than obviously weak van der Waals intermolecular forces. I was right on that, and what I was getting confused with was that when you're talking about biodegradability in terms of if you're trying to recycle these or let them be broken down, but under moist conditions with water or any type of base. These are easier to biodegrade, or they're more biodegradable because it's easier to break these bonds if you have a base, right? So they're easy to break. If you're using them as a plastic, for example, to in a you're throwing it away or dispensing of it, right? They're more biodegradable because it's easier to break down the hydrogen bonding if you have a base. However, if you're just using pure heat, like just pure heat, these are harder to break down if you're just talking about just pure heat, because the strong hydrogen bonding, compared to weak van der Waals molecular forces. However, if you're talking about biodegradability, like in a under room or normal temperatures, right, that you find in a landfill, that it's nothing to do about the temperature. It's more to do about the type of bonding and the type of compounds that you have in a landfill. And carbon or the additional polymers would be harder to break down, because they haven't got that electronegative oxygen atom. So it's much harder to it's much more difficult to break it down, and hence they're generally considered to be non-biodegradable. But when I'm kind of going through that process a little bit too much, I'll go through everything when I actually get to biodegradability. I don't want to confuse people too much, so just focus on what I've just been saying about the actual condensation polymers and actual bonding of polymers together. But in terms of the biodegradability, I'll actually make a video on that probably today or maybe later today. But yeah, I'm just gonna leave that part there so I don't confuse too many people about that. But what I said about the bonding, type of bonding, and differences in bonding is true. But anyway, nylon 66, right? So this is the other compound. So this is that's Kevlar. Also Kevlar, as you may have known from previous video, it's I would have talked about Kevlar. I'm pretty sure I talked about Kevlar. They use it. It's what they use in bulletproof vests. It's what they use. These bonds. Hence why I say it's such a strong bond. You can use it in bulletproof vests. This amide bond is actually it's a really strong bond you can use in bulletproof vests. And nylon 66 usually used in. I mean, you can use it in cling film. You can use it in cling film. It has other uses as well. But yeah, these are very strong bonds. Between with very strong intermolecular bonds and very strong intramolecular bonds as well. But when we talk about physical properties, yes, intermolecular bonds. Alright, cool. Before I start rambling too much on that, I'm going to cut through to the next part of this. So, synthesis of polypeptides, right? So, proteins or polypeptides are biopolymers formed from amide linkages. So they are a specific type of polyamide. So, they're just a type of polyamide, but they're a specific type of polyamide. And they're produced by condensation reactions between alpha amino acids. So alpha amino acids contain an amine and a carboxylic acid group at either end, and these two groups can react to form an amide linkage. These are the same bonds found between proteins as well as other examples. So I've pretty much gone through this in my previous example. Am I gonna? No, I've already gone through how to do. I'm not gonna go through that mechanism. But now I'm just gonna kind of I'm gonna summarize this kind of topic so far. So hopefully there's no questions about this. It's pretty much just the type of polyamide, but more specifically for between amino acids. So you know if you do biology, then you should be able to recognize that one. But yeah, so polymers, right? Why is that like that? Don't want that. Polyesters, so diols plus diol plus dicarboxylic acid. We also accepted derivatives. So yeah, we go for it. So polyesters, yeah, is between a diol and a dicarboxylic acid, or you could have derivatives, we'll say. And then we're talking about polyamides. Or we're talking about polypeptides. We're talking about the diamine and a dicarboxylic acid. Or derivatives. And that's it. Hopefully this video was helpful. Hopefully I didn't confuse you too much. If I did confuse you, let me know in the comments what part you were confused by, and I'll try and rectify that.